Okay. So, last meeting, ang diniscuss natin ay oscillations. Okay, so basically, ni-review natin yung concept ng oscillations na natutunan nyo from Physics 101. And we also introduced yung concept ng phase space or phase portrait or phase diagram in order to describe yung motion nung or trajectory ng object. Okay? Trajectory ng isang particle undergoing harmonic oscillations. So now we're going to add, ang hindi natin consider last time is damping. Okay? In other words, inassume natin na walang damping forces or walang damping force na involved dun sa oscillation na yun. Okay, like a simple harmonic motion, okay, hindi tayo naglagay ng damping force, so it just oscillates back and forth without any loss in energy or any loss in the amplitude of the oscillation. This time, in this meeting, consider natin yung oscillations with the damping force sa first part, and then sa second part, ang i-consider natin or idadagdagan natin to ng driving force. Okay? So yun yung gagawin natin ngayong araw. We'll begin with yung equation for the damped oscillations. Okay, before sa oscillations lang, we have mx double dot, okay, plus kx equals 0. This time we're going to add b x dot, na kung saan itong b na ito ay tinatawag natin na damping parameter or sorry, damping constant. Okay, and what we're going to do is we're going to rewrite this differential equation into this by dividing everything by m. Okay, now we define some constants, some new variables. Of course, itong variable na omega naught ay dinefine na natin before. So itong omega naught ay tinatawag natin na angular frequency ng oscillation. Nung particle, at itong beta naught ay tinatawag natin na damping parameter. Okay, so the angular frequency is just equal to k over m, and the damping parameter is just equal to b over m. Okay, from physics 121, okay, we can solve this differential equation. Okay, and when we solve this, ang technique natin dito is first hahanapin natin yung roots, di ba, ng auxiliary equation. So the roots for the auxiliary equation will be negative b plus b squared minus omega naught squared. And yung pangalawang root niya is negative b minus beta squared omega naught squared. Okay, ang general solution dito is x of t is equal to exponential minus beta t times a1 exponential ng beta squared minus omega naught squared t, okay, plus a2 exponential ng negative beta squared minus omega naught squared t. Okay. Of course, meron tatlong cases dito. Okay. Depende sa relationship between yung beta at yung omega. Okay. So, if omega naught squared is greater than beta naught squared, then we call that type of damping motion as underdamped. when omega naught squared is equal to beta squared, ang tawag natin dun ay critical damping. And when omega naught squared is less than beta squared, we call that over damping. Okay, anong itsura nung ano? Anong itsura nung oscillations? Okay, nung object pag underdamped or critically damped or overdamped. Okay, so we can see it here. Yung y-axis ay yung position, okay, which yung x-axis ay time. So pag underdamped, in the case ng underdamped, beta squared is less than omega naught squared. So ibig sabihin yung damping parameter is less than the frequency of oscillation. Kita natin na nag-oscillate siya at x equals at the equilibrium position. Remember that x equals 0 is the equilibrium position. And yung underdamping, yung case ng underdamping, we see that the particle oscillates through the equilibrium position. Okay, so nag-oscillate siya back and forth. Okay, pero ang difference nito dun sa original or sa case na walang damping is that yung amplitudes ay bumababa as a function of time. In the case of critical damping, kung saan yung beta squared, yung damping parameter is equal to the um, angular frequency of oscillation, then ang mangyayari lang dito is parang babagsak na lang kaagad to zero, mag-approach to zero in the faster than the case of in the case of overdamping. Okay, so pag overdamping naman, when beta squared is greater than omega naught squared, then you still, or yung oscillation or yung motion ng particle just approaches to zero. Okay, pero it approaches to zero at a very, very long, over a very long period of time. Now, for critical damping, makikita nyo na, for critical damping and for overdamping, makikita nyo na wala talagang oscillations. Okay, just the particle just moves from its initial position towards the equilibrium position. Okay, and in that case, tama pa ba na tawagin natin na, ano, na yung omega is the angular frequency of oscillation or nag-oscillate ba talaga tong frequency na to? Well, technically hindi. Okay, pero for the purposes of tawag dito of yung mathematical treatment natin dito, we still call it an angular frequency. Okay, sa real life, sa tunay na buhay, kailan tayo nakakita ng underdamped, critically damped at saka overdamped na situation? Of course, yung underdamping, parati nating nakikita yan sa spring, di ba? So or sa pendulum even. Okay, so if you have a pendulum na nagsisway back and forth, nakikita natin na as time passes, okay, yung nag-oscillate siya through the equilibrium position, pero yung amplitude niya paliit na paliit. Okay, so that's an example of an underdamped situation. What about for critical damping? Well, kung nakasakay na kayo of course nakasakay na kayo sa isang vehicle, especially sa bus, okay? Okay, mapapansin nyo na in some instances, okay, in some cases, pag yung bus ay dumaan, for example, sa isang pothole or sa isang ang tawag dito, hump, okay, mapapansin nyo na, syempre, mararamdaman nyo na umangat yung bus and then bigla na lang titigil yung tawag dito, yung pag-angat niya, babagsak siya kagad without any oscillation. Okay, so that's the case of critical damping. Okay, for overdamp, okay, ano bang magandang example? Well, in this case, if the spring dun sa mga vehicles yung ay sobrang taas ng spring constant, then you will expect na mabagal. Okay, so mabagal yung case ng pag balik niya sa equilibrium position. You can also see an example in overdamping when an object passes through a fluid, for example, like water, di ba? So halimbawa, meron kang heavy object na nilagay mo dun sa water. Of course, that experiences yung object na yun experiences yung buoyant force due to the water, and of course that object doesn't oscillate, so it just goes towards yung motion niya just goes towards the equilibrium position. Okay, so that's the case or those are examples of overdamping. And itong picture na to describes yung motion ng overdamp, underdamp, tsaka critically damped na particles. So if we compare yung underdamping, okay, with yung anong tawag dito, with yung no damping, okay, ito yung graph na magpapakita nun. So what we have here, so pag beta is equal to 0, this means na wala yung damping parameter. Ibig sabihin walang damping, di ba? You can see this dashed line, and you can see that it's just oscillating without any change in amplitude. Okay, and when there's underdamping, makikita nyo na nag-oscillate pa rin siya, pero yung amplitude niya nagbabago. Okay, and what you can also observe if you look at it, if you look at this carefully, kung titignan nyo, hindi nag-intersect. Yan, dito mas obvious na. Okay, hindi nag-intersect yung uh, wave functions, okay, at the same points, okay, when you compare beta is equal to 0.2 omega naught and beta is equal to 0. Okay, so in other words, pag beta is equal to 0, yung omega naught ninyo is constant, right? Pero pag meron ka ng damping, yung omega naught ninyo, or in this case, some other frequency, okay, na makikita natin mamaya, it's actually longer. Okay, or the time it takes, the period, di ba, is actually longer. So the frequency is shorter. Okay, kumpara sa kung walang damping. In addition, yung amplitude nga niya ay lumiliit, and yung amplitude niya is described by this exponential minus beta. So in essence, if you go back to this equation, okay, this describes itong part na to na nasa square brackets describes yung oscillation. And itong part na to na may exponential describes yung decay. Okay? Okay. Makikita niyo naman na yung oscillation, okay, na ito ay oscillating kasi 'di ba? Essentially ang exponential x plus exponential negative x is somehow related to cosine, or in this case cosine hyperbolic of theta. So it's an oscillating function. But because we're multiplying it by the exponential of minus beta, then it oscillates. At the same time, it also decreases at this rate. Okay, so sa rate na ito. Okay. Okay. So let's first consider yung underdamped motion. Okay. So pag underdamped, okay, so pag underdamped, okay, we start from this equation x of t is equal to exponential minus beta t a exponential square root ng beta squared minus omega naught squared t. Exponential, A1 ba yun? Okay, exponential square root ng beta squared minus omega naught squared t plus A2 exponential minus square root ng beta squared minus omega naught squared t. Okay, now we define a new parameter omega naught to be equal to the square root of beta squared minus omega naught squared, so that we write the position of the particle undergoing underdamped motion as negative exponential negative beta t times a sub 1 exponential negative or positive omega 1t plus a2 exponential negative omega 1. Okay. And in this case, since sinabi nga natin kanina na ito ay na yung exponential plus omega 1t plus exponential negative uh, omega 1t is related to cosine, so we can actually rewrite this as exponential beta t times yung amplitude times cosine omega 1t minus some phase constant. Okay, so ang tawag natin dito is the angular frequency of the damped oscillator. Now, again, tulad nung nakita nyo kanina dun sa figure, hindi ito a constant na value all throughout. Okay, and technically hindi nga natin siya pwedeng tawaging hindi rin to natin pwedeng tawaging angular frequency in the sense na ano no na dun sa case ng walang damping. Okay, kasi lumalaki yung frequency niya, di ba? So, but in the case of small time tawag dito, small time intervals, okay? Pwede nating i-assume na yung omega 1 na yun ay constant, okay, with respect to time. Okay, so in most cases naman when you have a tawag dito, damped oscillation, in most examples have oscillations that occur over a very short period in time. Okay, yung simple pendulum is not it's not the case kasi sa simple pendulum, 'di ba matagal, it takes a minute or so hanggang sa or even longer hanggang sa mawala yung or hanggang sa mag-zero siya, 'di ba? But for example, yun nga sa shock absorbers ng mga vehicles, okay, pag nasa likod ka ng bus, um, may mapapansin mo na it just takes 1 or 2 seconds until mawala yung oscillations. And those are the cases that we consider sa underdamped motion. And in that case, we can assume an angular frequency of omega 1, okay, para dun sa ganun klaseng types ng oscillation. Okay, and like we said earlier, so this describes yung ang tawag dito yung decay of damping. Okay? And this describes yung oscillation. Okay? Okay. Now, if we go here, we can also describe yung ratio ng amplitudes nung damping. Okay, ang ibig ko sabihin is this. So, let's say that I take the amplitude at this point and I take the amplitude at this point. Okay, so yung amplitude dito sa point 1, for example, is A exponential minus beta t. Okay, let's say that's at time t. Okay, so yung time dito is t and yung time dito is t plus some parameter tau. Okay, and at this time, so that's a exponential minus beta t plus tau sub 1. Okay, and of course, this term cancels out. Okay, itong term na to at saka itong term na to cancels out. And of course, yung a matitira. And we get exponential beta tau 1. Okay, and in this case, ang tawag natin dito is the decrement of the motion. Okay, it's nothing but yung ratio, okay, nung amplitudes for each time interval. Okay, beta tau 1 is called the logarithmic decrement. Okay? Okay. Questions? Okay, so let's consider this example. Okay. So construct a general phase diagram analytically for the damped oscillator. Okay, then using a computer, make a plot for x and x dot versus t and the phase diagram for the following values. A equals 1 centimeter, omega naught equals 1 radians per second, and beta equals 0.2 per second, okay, and delta equals pi over 2 radians. Okay, first let's set up yung yung ating equations. Okay, so oops. Okay, so alam na natin yung x, yung position x. Okay, sinulat na natin yun to be a exponential minus beta t times cosine omega 1 t minus delta. And remember that omega 1 is just the square root of beta squared minus omega naught squared. Now, if we take the derivative of the position, then we get the velocity. Okay, so we have a exponential minus beta t, okay, times beta cosine omega 1 t minus delta. Okay, that's if that's when you take the derivative of the exponential. And then when you take the derivative of cosine, we have omega 1 cosine, or sine, sorry. And sine omega 1 t minus delta. Okay, and of course, there's a negative sign in front. Okay. Okay. Okay, may negative sign dyan kasi dyan galing yung negative. And of course, when you take the derivative of cosine with respect to time, then you get the negative, you get negative sign. Okay? So, yan yung dalawang expressions that we need to describe yung anong tawag dito, yung oscillations or yung phase diagram. So we plot this, okay, and take a look at what it looks like. Okay, so at this point, I'm going to stop sharing this slide and start sharing yung MATLAB code for this. Okay, so let's see. Lagyan natin konti. Let's do this. Okay, so ito yung problem. Okay, construct a general phase diagram. Okay, for that we need the following equations. Okay, x of t equals a exponential minus beta t cosine omega 1 t minus delta, where omega 1 is equal to square root ng omega naught squared minus beta squared. Okay, and then x dot of t is equal to negative a exponential minus beta t times beta cosine omega 1 t minus delta plus omega 1 sine omega 1 t minus delta. So yan yung ating equations. So this simply defines, of course, ito yung mga constants, by the way. Okay, and this simply defines yung omega 1. This is the time. Okay, yan ang ginamit kong time para lang, which is the same as what we have in the book. Okay, then pinlot ko lang itong x, o nilagay ko yung x na equation, and then nilagay ko yung b na equation. Okay, and then of course, pinlot natin yan. So when we plot it, we get this expression, or this graph. Okay, yung blue dito corresponds to position, and yung red corresponds to the speed. So anong nangyayari dito? At t equals 0, the object, the particle is at the equilibrium position. Okay, but it has a velocity. Okay, so meron siyang positive na velocity. Since positive ang velocity niya, mag-move towards the positive axis yung particle. Okay, and as it moves, yung velocity, well, actually, yung velocity pala ay negative. Well, may magnitude siya, pero negative yung direction. So, it actually decreases, okay, as it moves, the velocity decreases, okay, and at this point, okay, na kung saan maximum yung kanyang speed, yung position niya, sorry, maximum yung position niya, yung speed niya is equal to 0. Okay, and from there, magmo-move yung particle pabalik sa equilibrium position, and it does that because merong restoring force towards the equilibrium position. And since merong restoring force, mag-increase ulit yung velocity but towards the opposite direction. So negative yung direction ng velocity dito. Okay, and then at this point kung saan maximum yung velocity, yung particle will be at, oops, ano to? Maximum yung velocity ng particle, yung particle will be, well, it says here na yung particle is somewhere here, okay, but that's okay kasi nga this is damping, okay, ang tawag dito, this motion is damped, and it actually reaches the equilibrium position at some velocity, okay, which is not the maximum velocity. Okay, so nandun pa rin yung behavior, yung interaction ng position at saka velocity na ang ginagawa ng force is hinihila niya towards the equilibrium position yung particle. At the same time, nagdi-increase tsaka nagdi-decrease yung velocity, and nag-change siya ng direction depende sa kung ano yung nangyayari sa kung ano yung driving force. Okay? Now, here, this is the graph of position and speed versus time. If we plot the speed versus position, then we get our phase plot. Okay, dito sa phase plot, okay, okay, let's see, increase natin konti yun. Kailangan ko atang i-run. Okay, so increase natin ng konti yung, oops. Okay, okay, ayaw siya zoom. Anyway, so the particle starts here. Okay, small, sorry. The particle doesn't start there. Okay, ulitin ko. Sorry. Kasi it has an initial position. Ang initial position niya is here. Okay, ito yung initial position niya, and what happens? Okay, so remember that the y-axis corresponds to the speed, and anything above 0 is positive, and anything below 0 is negative. Dito naman, yung x-axis is position, and anything above 0 is positive, or above the equilibrium position, and anything below 0 is negative. It's below the equilibrium position. Okay. So here we start at the equilibrium position, okay, which is the same as yung graph kanina. Okay, and the particle has a positive velocity. Okay, as it moves, okay, as it moves towards the maximum position, okay, ito na yung maximum position, then we get zero velocity. Okay, so zero yung velocity at the maximum position. Okay, now the direction of the velocity changes, okay, as the particle goes back to the equilibrium position. And makikita natin na pagdating niya rito at the equilibrium position, the speed of the particle is not actually maximum, okay? Okay, but it's actually a little bit less than the maximum value, but it's still, the speed of the particle is still negative. Okay? Then ang mangyayari is mag-move away from the equilibrium position yung particle due to inertia. Pagkatapos, it will reach this equilibrium position, it will reach this maximum position dun sa kabilang side when the speed of the particle is 0. So it goes through that motion, positive velocity, and then tawag dito, positive velocity, but this time makikita nyo na yung maximum velocity is not necessarily at the equilibrium position. In fact, yung equilibrium position na dito, okay, yung speed is less than the maximum speed, okay, dun sa equilibrium position. Then it goes away from the equilibrium position towards its maximum position where the velocity is again 0. Okay, so this is how you interpret the phase plot. Okay, so it goes into this motion. Okay, it's still periodic motion, pero since the amplitude is decreasing, makikita nyo nagdi-decrease yung amplitude. Ito, doon, dyan, dito, doon, doon, doon. Okay? So nagdi-decrease yung amplitude as time passes. Okay. Okay, so yan yung nangyayari dyan sa yeah, that's how you interpret a phase plot. Now if we plot the energy versus time, okay, we get this. Okay, so the energy is the blue curve, and the rate of energy loss or gain is the red curve. Okay. Now, this energy was simply, tawag dito, was simply plotted using this equation. So, supposedly merong 1/2 mv squared dito, pero ninormalize ko na to, okay, nilagay ko yung 1/2 dun sa side ng E, and then yung m nilagay ko rin sa side ng E. Okay, so para lang para hindi na natin i-consider yung mass ng object. Okay, constants lang naman sila, so it doesn't matter. Ang gagawin lang naman ito is, i-shift nyo lang naman yung value. Okay, pero yung behavior will be exactly the same. And then I also took the derivative of E with respect to time. So this is the equation, or the code that I use. Okay, and what we get is this one. Okay, so we have this expression, this behavior, okay, na yung energy ay meron pa ring sinusoidal na behavior, okay, oscillating behavior, pero yung energy ay nababawasan as time passes. Okay? Now, DE/dt explains the losses, or it shows the loss of energy. So, dito makikita natin yung maximum loss. So, ito yung maximum loss of energy somewhere here. Okay? And dito makikita din natin yung maximum gain in energy. Dito naman maximum loss of energy. And for each oscillation or each period, nawawala yung energy, and the energy that is lost is dissipated somehow to some other form of energy, typically heat. Okay, so this is what happens, okay, when the particles undergoing a damped oscillation. Okay. Okay, so we go back here. Of course, i-share ko sa inyo yung code na yun para lang meron kayong, kung interesado lang kayo na tignan at paglaruan. Okay. Let's see, nasa na ba tayo? Okay, so nagawa na natin itong na to, so itong part na to. Okay. Construct a general phase diagram, which you already did. Okay, and dinescribe natin yung phase diagram na yun. Okay, base dito sa mga equations na ito. Okay. Okay. Now let's go to, oops. Okay. Now let's go to critically damped motion. So pag critically damped motion, okay, omega naught, beta squared pala is greater than omega naught squared. Okay, and in this case, yung solution natin reduces to A plus BT exponential minus beta t. Okay? And nakita naman natin yung motion na yon. So this is actually just a linear term, okay? It doesn't describe yung ano, yung ano, it has no oscillatory behavior at all, di ba? And this is the decay term, okay? So if you graph yung linear and then you multiply it by a function that is decaying, okay, like an exponential, okay, like that. So ang mangyayari lang dyan is uh, something like this. Okay? So ganun lang yung mangyayari. Okay, so that's the product, okay, of blue and orange. Okay, so ito yung nangyayari. So linear component and yung decay. Orange. Okay, so we don't have much to say about that kasi it's pretty straight forward and for practical applications wala tayong ganong pinagagamitan ng ganitong klaseng motion. Okay? Um, Now we can proceed to overdamp motion. Okay, na kung saan okay, sorry. Ano bang sinasabi ko? Critical critical damping is equal, hindi zero. Ay, hindi greater than equal. Pag overdamp na motion, then we have beta squared greater than omega naught squared. Okay, and in this case, we still have this expression of x of t exponential minus beta t times a1 exponential omega, let's say omega 2t, okay, plus a2 exponential negative omega 2t na kung saan yung omega is still beta squared minus omega naught squared. Okay, so naglagay lang tayo ng bagong parameter na omega 2. Okay, para lang i-describe yung anong tawag dito? Yung para i-differentiate siya from the angular frequency dun sa underdamped na case. Okay, so um, if we solve for the derivative of this function, okay, of the position, then we get a1 exponential minus bt exponential omega 2t plus a2 exponential minus bt exponential minus omega 2t. Or pwede natin ito isulat sa a1 exponential minus b minus omega 2t plus a2 exponential minus b, oops, plus omega 2. Okay, and sorry, hindi pa pala yung derivative. X lang yan. Okay, and then if we get the derivative, yun kung konti. Baka kulangin sa space. If we get the derivative, then we have a1 negative beta minus omega 2t of omega 2 times exponential minus beta minus omega 2t, okay, plus or minus a2 beta plus omega 2 a times exponential minus beta plus omega 2 t. Okay. Okay, so of course beta um, mathematically, pag tinake nyo yung square root nito, okay, this is actually a square root of a plus or minus square root, di ba? So if we consider one case like, for example, omega 2, by the way, since ito yung case, no, it can be na yung beta squared is greater than omega naught squared. So omega 2 simply reduces to plus or minus beta. Okay, plus or minus beta. Okay, and in the case na kung saan omega 2 is equal to plus beta, then this disappears at ito yung magdo-dominate. Okay, and in the case na yung omega 2 is equal to negative beta, then this disappears at ito yung magdo-dominate. Okay, and binabanggit ko lang yan kasi when we do the phase plot or when I show you the phase plot later, there's this asymptotic lines corresponding to this case. Okay, so ito yung phase plot nung overdamped na particle. Okay, and yun na nga, makikita nyo na may dalawang lines doon corresponding to the asymptotes of um, the motion of the particle and the speed of the particle. Yung particle na yan, never, since asymptote nga siya, no, it doesn't behave in such a way na mag-overlap yung or i-overlap niya yung mga asymptotic lines na yan. Okay, so there are always those lines. But we can take a look at three cases, okay, na kung saan yung motion ay above the asymptote. So like yung case 1 at saka case 2 is above this asymptotic line, and yung case 3 is below this asymptotic line. Okay, so let's take a look at yung case 1. Okay, by the way, yung mga dots na yan, yung mga dots na nakikita niyo diyan, yan parati yung initial positions. Okay, so these are cases that show like 8 or 9 initial positions. Okay, and we're going to consider 3 of them. Okay, so let's consider case 1. Okay, yung case 1 ay kung saan yung x is greater than 0 and x dot is also greater than 0. Okay, so ang makikita natin dito is it starts from this position. Okay, then it goes towards the maximum value here. Okay, and at the maximum value, the velocity is 0. Okay, the maximum value, the velocity is 0. Then the velocity changes direction as the object moves towards the equilibrium position. Okay? But pagdating sa equilibrium position, papansin nyo na yung magnitude ng velocity, yung speed also decreases. Okay? Lumiliit yung amplitude na yung ano na to, yung space na ito, which implies na yung speed ay nagdi-decrease habang nagdi-decrease yung position niya. So at pagdating niya sa point na to, 0 na yung velocity and 0 na rin yung position. So ang mangyayari is it just increases kung ito yung x-axis ninyo, di ba? So mag-move lang siya towards the maximum position and then pabalik sa equilibrium position where it stops. Okay, yan yung case 1. Yung case 2 naman is when x is greater than 0 and x dot is less than 0. So negative yung velocity. In this case, magsa-start pa rin siya. Okay, so gawin natin green yan para lang ma-differentiate. Okay, in this case, magsisimula pa rin siya from this position, but it no longer goes to the maximum position. Okay, just goes straight to the equilibrium position. And as it goes towards the equilibrium position, makikita nyo na yung magnitude ng velocity, yung speed niya also decreases. And pagdating nila sa equilibrium position, the speed will be 0. Okay, so yung mangyayari na motion niya is, halimbawa ito yung equilibrium position nandito. Okay, and andito siya nag-start, so biglang gaganon lang siya. Okay, so ganun yung mangyayari. If the velocity is 0, and the position is negative. Initial position is negative. Okay, and now let's take a look at when the position, okay, is also positive, pero yung velocity okay, is negative, okay, pero nandito siya below this asymptote. Okay, so ang mangyayari dito is, um, of course, mag-move ito sa equilibrium position. Ito yung equilibrium position at x equals 0. But it still has some speed. Okay, so meron pa siyang speed at the equilibrium position. So this is contrary to what we expect, di ba, hindi, meron, pero hindi maximum yung speed. Okay, ito yung contrary dun sa ine-expect natin pag walang damping. Okay, and then the speed decreases. Okay, at the same time, the position increases, okay, pero dun sa kabilang axis, towards the other side, until it reaches a maximum position, at which point yung velocity again is 0. Okay, then, yung particle goes back to the equilibrium position, and at the same time, mag-change ng direction yung velocity, mag-increase siya slightly, and then it decreases along with the decrease in position. Okay, so parang ang magiging motion niya is if this is the equilibrium position, okay, and nag-start siya at some position dito na lang sa gitna yung equilibrium position. So ito yung equilibrium position, and then nag-start siya sa somewhere here, okay, somewhere here. So meron siyang speed, okay, speed na gano'n, and then dahan-dahan siyang babalik dun sa equilibrium position. Okay, so mabilis, and then balik sa equilibrium position. So that's yun yung iba't ibang scenarios nung overdamp na motion. Okay, now you can also study yung iba't ibang yung ibang initial positions and take a look at ang tawag dito kung anong nangyayari sa kanila. Okay? So, any questions? Okay. So let's consider a pendulum of length L and a bob of mass M at its end. Figure 3-13. 3-13. Hindi ko pala nilagay yung figure. Oh, oo nga, hindi ko nilagay yung figure. Okay. Let's see. I'll quickly show you yung figure lang na yun para lang may idea kayo. Okay, and okay, so ito yung figure 3-13. Okay. Zoom. Okay, so ito yung pendulum. Okay, meron siyang length na L. Okay, tapos yung mass niya is, or yung weight niya is mg. So ito yung component ng weight, di ba, along this axis. And then meron itong damping force described by this equation. Okay, so yung bob na ito is tawag dito, nag-oscillate, and dahil immersed siya in a fluid, okay, ang mangyayari dito is ma-experience itong damping force, okay, dahil sa fluid. And we take a look at what's happening in this case. Okay, so going back dun sa problem or sa slides. So we have this problem. Okay. So sabi rito is merong pendulum, okay, na merong length L and a bob of mass M moving through oil. Yung fluid dito is oil. The massive bob undergoes small oscillations, but the oil retards the bob's motion with the resistive force, okay, proportional to the speed. Okay, so yung expression for the resistive force is 2m square root ng G over L, theta dot. The bob is initially pulled back at t equals 0. So, ibig sabihin, hinila muna siya with theta equals alpha and theta dot equals 0. So, binitawan lang siya without applying any force dun sa initial na position niya. So find the angular displacement theta and velocity theta dot as a function of time and sketch the phase diagram. Okay, so in this case, since ito ay oscillatory motion, okay, since ito ay pendulum, okay, we treat this as, or we write the differential equation in this way: ml dot ml theta double dot is equal to mg sine theta. Okay, and this is the case when there's no resistive force, diba? Ang ginagawa nyo before, pag walang resistive force, is that you have this mg, and then you have this component which is mg sine theta, and then you have this, hindi na natin kino-consider yung tension in this case, but if this is theta. Okay. So yun yung nangyayari. Hmm. No, hindi yan ang mg cosine yan. Okay, so this is mg cosine theta. mg cosine theta. mg sine theta is this one. So that's mg sine theta. Okay, bakit ito? Kasi yan ang force na magre-restore sa pendulum dun sa equilibrium position. Okay, and it's negative because when the angle is positive, the force is negative because it points towards the equilibrium position. And pag nandito naman yung angle, when the angle is negative, the force is positive. So yung force at saka yung angle is negative of each other. And of course, this is just from Newton's laws of second law ni Newton na MA, di ba? MA or MX double dot. Okay, since ang X ay equal sa R theta, then X double dot ay equal sa R theta double dot. Ang R dito is yung radius, but in this case, it is the length of the pendulum, so ML theta double dot equals sa M minus mg sine theta. Then we add the tawag dito, resistive force. Okay? So the resistive force, okay, is equal to minus, ano lang nakalagay? Ito, minus 2m square root ng g over L times L theta dot. Okay. Okay. So yan yung resistive force. Now, if we simplify that, okay, let's say divide everything by ML naught, divide everything by M, so mawala yung M, di ba? And then divide everything by L, then we get negative G over L sine theta. Okay, wait. Minus 2 G over L, cancel yung L na yun, then theta dot. Okay? And if you move everything to the opposite side, minus 2 square root ng, or plus 2 square root ng G over L theta dot plus G over L sine theta is equal to 0. Okay, then we use the small angle approximation. So for small angles, sine theta is approximately equal to theta. So our equation then reduces to 2 square root ng G over L theta dot plus G over L theta is equal to 0. Okay, so in this case, we can now compare this to our differential equation kanina, okay, for one-dimensional motion na may damping. Okay, this becomes omega naught squared at itong term na ito becomes beta. Okay, so beta squared, omega naught squared, if you write it, is G over L, and beta squared is equal to G over L. Okay, sorry, hindi kasama yung 2 dito. Yung ano lang kasama. Yan lang yung kasama, G over L. Okay, so, anong napansin natin? Omega naught squared is equal to beta squared. Okay, so anong klaseng motion ito ngayon? So this motion corresponds to the motion that is critically tapped. Okay. And how do we describe this motion? Yeah. So of course we need to plot a phase diagram, and it's actually one of the things that nare-require dito. Okay, so sketch the phase diagram if GL square root of GL is equal to 10 per second and alpha is equal to 10 to the minus 2. Okay. Wait, ano ang alpha? Meron yata akong na-miss. Ano ang alpha? Okay, yung initial condition. Okay. Theta is equal to alpha. Okay, so yung initial condition for the angle is 10 to the minus 2 radians at t equals 0. Okay, so ano ang itsura nung phase diagram nito? Of course, you will need a computer to show yung phase diagram. Oops. Well, ito muna. Position is looks like this. Ah, so hindi yan, iba yan. Okay, hindi ko na naman nalagay. Okay, sorry about that. So, let's go back here. Okay, so now we have this graph, okay, for the phase diagram. Okay, so dito ang x-axis is theta, the angular displacement, and the y-axis is the angular velocity. Okay, and if we assume an initial position, okay, which is theta 10 to the minus 2, di ba? 0.01, ito yung initial position niya. Okay. Anong mangyayari dun sa particle? Okay. So the velocity here is negative or zero at this position. Okay, and due to inertia, magmo-move yung particle towards the equilibrium position. Pero as it moves dun sa short distance, okay, na nag-move yung particle, okay, towards the equilibrium position, biglang mag-increase yung speed niya. Okay, towards dun sa opposite direction. Okay, and it reaches a maximum, okay, over this short tawag dito, space. Over this short space. Okay. So mabilis yung speed niya rito. Mabilis dito and then babagal, dahan-dahan dito. Okay, and as you can see, as the particle goes to the equilibrium position, the speed also decreases in amplitude. Okay, the speed also decreases. Okay, and at x equals 0, the speed is also 0. Okay, so now this is what happens when it's critically damped. Okay, so ano mangyayari dito? If we move it at this position, if we place it at this initial position, speed increases, okay, over small space, di ba? Speed increases and then dahan-dahang mag-move towards the equilibrium position. Mabilis and then dahan-dahan. So ganun yung nangyayari dyan. Okay, sa example na ito. Okay. Yes. Any questions? Okay. Any questions? Wala? Okay. Bigyan niyo na ako ng 2 minutes. Tinatawag ako ng kalikasan. Okay. So now, nakita na natin kung anong effect ng damping force. Let's add something dun sa differential equation. And what we're going to add is yung driving force. Specifically, we're going to add a sinusoidal driving force. Okay, so we have this differential equation earlier, plus kx is equal to, originally, nung kanina, zero yung ano natin dyan, yung consideration natin dyan, di ba? But this time, we're going to add a sinusoidal na damping force. Okay, yung oscillation nung damping force na ito is tawag dito is described by this um, tawag dito angular frequency omega, and then yung lakas ng force na ito is described by this force na F naught. Okay, so of course ang isang example ng system na merong driving force is, 'di ba, pag nakasakay kayo sa swing, okay, tapos meron tumutulak sa inyo. And pag nasa swing kayo, 'di ba, kung walang tumutulak, ang mangyayari lang is mag-move lang yung swing back and forth hanggang sa anong tawag dito, hanggang sa titigil na yung swing. And hindi yun masaya, right? Para sa isang bata. So, ang kailangan nyo is meron tutulak. Gusto nyo na may tutulak sa inyo dun sa swing. And yung pagtulak na yun is described by this driving force, F naught cosine omega t. Okay, so yung lakas ng pagtulak is F naught, and yung frequency ng pagtulak is yung omega. Now, imagine yun na kung yung frequency ng oscillation is not the same as yung frequency ng pagtulak, of course, sira yung ano, 'di ba? Sira yung motion. Kailangan nagma-match yung frequency ng oscillation dun sa frequency ng pagtulak para magkaroon ka ng continuous na motion. Okay, so that's one way to complicate a ride which is as simple as a swing, di ba? So that's one way to describe a swing. Okay, so sa 1-to-1, paano ba natin sinosolve itong differential equation na ito? Of course, if we divide first everything by m, okay, then we end up with this kx is equal to a cosine omega naught t, and we still have beta equal to b over m, and k over m is equal to omega naught squared. Okay, and a in this case is f naught over m. Okay, and omega dito is the oscillation of the driving force. Okay, frequency of the driving force. Okay, so we have two solutions dito. Paano natin ginagawa ito sa 1-to-1? So first, kinukuha nyo muna yung solution na kung saan zero yung right-hand side, di ba? And that's the complementary solution, the complementary function. And we already know what that is. Okay, so that's a exponential minus beta t. Sorry, walang a dun. Times a1 exponential omega 1t plus a2 exponential minus omega 1 t. Okay, na kung saan yung omega 1 ay equal sa square root ng b squared minus omega naught squared. Okay, then for the particular solution, ang ginagawa natin is nag-assume tayo ng solution which has the same form as the driving force. So we have x pt, okay, equals to d cosine omega t minus delta. Okay, and if we do that, we substitute xpt dun sa ating differential equation. Okay, what we get, okay, so substitute natin yan dyan. Okay, so what we get is this expression, okay, which is a minus d times omega naught squared minus omega squared cosine delta plus 2 omega beta sine delta cosine omega t minus d omega naught squared minus omega squared sine delta minus 2 omega beta cosine delta sine omega t is equal to 0. Okay, so we have ano yung delta na yan? Yung delta is actually 2 omega beta divided by omega naught squared minus omega squared. Okay, and okay, and from this equation we can actually solve for d. Oops, kailangan ko lang isa pa. Okay, we can solve for d. So d, the amplitude d is equal to a over omega naught squared omega squared cosine delta plus 2 omega beta sine delta. Okay, or if we write that in this way, square root ng omega naught squared minus omega squared squared plus 4 omega squared beta, okay, beta squared. Okay, so if we do that, then we get this particular solution, which is equal to a over the square root of omega naught squared omega squared squared plus 4 omega squared beta squared cosine ng omega t minus delta. And of course, delta here is defined as tangent inverse nung nakuha natin kanina, 2 omega beta minus omega naught squared omega squared. Okay. So, at this time, hindi na natin kinonsern yung sarili natin sa mathematical steps. Okay, so we just proceeded dun sa final solution. So the general solution is x of t is equal to xct plus xpt. Okay? So ano ang binibigay sa atin ito? Okay, remember that xc is given by this at yung xp is given by this. Okay? So anong masasabi natin about that? Okay, so again, this gives us yung decay, di ba? So alam naman natin ang itsura niyan. Ang itsura niyan is a sinusoidal function na nagde-decay. Right? So it's a transient effect. Transient in the sense na it's totally dependent, or the behavior is totally dependent on what is happening to it over time. Okay, in this case, ito ang tawag natin dito is yung steady state. Steady state effect. Okay, even though mayroon tayong expression for time dito, but it's a cosine function, di ba? So it has this tawag dito oscillating behavior without any decay. So i-add nyo itong dalawang solution na yun para makita ko ano yung magiging behavior ng system. Okay, and if we consider this graph. Okay, so this graph is an example, okay, of a particle driven by an oscillatory force, okay, with damping. Okay, and makikita natin dito yung XP at saka yung XT. So yung XP is this one, itong dark line, and then yung XCT is yung tawag dito yung complementary solution. So kitang-kita natin na yung XCT has this decaying diba? Sinusoidal na function, pero yung XPT has this oscillatory na function na hindi nagdi-decay. And this is for the case na kung saan yung beta is equal to 0.15, but more importantly, yung omega, which is the frequency of the driving force, okay, is greater than or is equal to 1/7 of the of the angular oscillation of the transient or the complementary solution. Okay, so itong frequency na ito, yung frequency na yun ng transient solution, okay, is 1/7 of this frequency. So yan. Yan. Okay, so pag maliit yung, di ba, maliit lang yung frequency. Okay. Maliit yung frequency kumpara dun sa frequency nung nung transient solution, di ba? Or uh, nung transient component. So ito yung transient, di ba, nababawasan yan over time. Pero then meron kang driving force, di ba, na mas mabilis. Sorry, mas mabagal. Mas mabagal yung driving force kasi yung frequency niya is just 1/7, di ba? So ganito ito, tapos mabagal yun dito, di ba? Every 7 nito, may meron kang isang ganon. Ganito yung nangyayari. And of course, if you add both of them, ganito yung magiging behavior, di ba? So medyo erratic dun sa simula, di ba? Kasi nga sa simula lang naman niya magkakaroon ng effect somewhere here. Okay, kasi at this time, okay, nawala na yung transient na effects dahil nag-die down na yung transient na effects. And this will just be continuous sinusoidal na function. Okay, now, sinabi natin na sa slide, sa swing, diba? Para ma-match nyo yung pag swing uh, nung bata, okay, kailangan yung angular frequency ay nagma-match din sa pag-swing niya. So dapat omega, which is the angular frequency of the driving force, should be the same as omega 1, which is the angular frequency of the swing. Okay, and pag nagma-match yung dalawa na yon, in that case, we call that resonance. Okay, and to derive yung resonance frequency. Okay, so what we do is we take this amplitude. Okay, we take this amplitude D. Oops. We take this amplitude D and we take the derivative of that with respect to omega. Okay, and set it to 0 to find the resonant frequency. Okay, so ang sinasabi ko is take the derivative of that with respect to omega and then set it to 0 where omega is equal to omega r. If you do that, you'll find that omega r is equal to square root ng omega naught squared minus 2 beta squared. Okay. Okay, so anong una natin makikita rito? If omega naught squared minus 2 beta squared is greater than, or ang condition dito dapat greater than 1 siya, di ba? Or greater than 0, sorry. Greater than 0. Okay, otherwise, imaginary yung square root and you don't have a solution or you don't have a physical interpretation for an imaginary oscillation, right? So, omega naught greater than 2 beta squared, okay, or omega naught greater than the square root of 2 beta. Okay, so ito yung condition, tawag dito, minimum condition para magkaroon ka ng oscillation. Okay? O ng resonance. Okay, and if that doesn't happen, then wala kayong resonance. Okay? Okay. Now, we can describe yung resonance through what's called a quality factor. Q. So omega R divided by 2 beta yung expression natin for the quality factor. Okay, and in practicality, paano ba natin i-interpret ang beta at saka omega not, omega R? Well, of course, hindi natin ma-interpret ito as is. So we have to like take a look at what is happening, okay, sa system. Okay, and if we take a look at this graph, for example, okay, this graph shows yung iba't ibang values, okay, ng D as a function of omega. Okay, and we can see that at omega naught, okay, nandoon lahat nung naka-peak lahat nung D, right? Okay, and ibig sabihin tawag dito maximum yung D niya, or yung quality factor niya is also or yung maximum yung D, or nasa resonance, okay, yung system. Okay, and you can also see na nag-iiba yung graph ng D with respect dun sa quality factor. So for Q equals 0, okay, you'll see na ito yung graph, medyo flat. Okay, in Q equals 1, nagsimula na siya mag-peak, and then as Q increases, okay, nagpi-peak siya na nagpi-peak. Now, where's beta in this case? Diba? Sabi kasi natin kanina na ang quality factor is omega R over 2 beta. Well, if you have this graph, then this actually reduces to omega naught over delta omega. Okay, na kung saan yung omega naught is this, okay? Yung resonant frequency, okay, and yung delta W, delta omega is the full width at half maximum. So, ano ibig sabihin yan? If we take this graph, ito yung maximum ng graph na to. So, anong Q to? Q equals 13. So, Q equals 13, yan yung maximum niya. Kunin niyo yung kalahati niyan. So, ang kalahati niyan is somewhere here, I suppose. Okay, and then, yung kalahati niyan has this width. Okay, yung width na yan yung delta W. At yan yung insert niyo doon. Okay, so that's how you describe yung quality factor. So makikita nyo na as the width decreases, the quality factor increases. And that's what you see here, di ba? Dito, yung width ay sobrang lapad, but the quality factor is low. And dito, the width is so small, that's yung quality factor ay sobrang taas naman. The second graph shows you yung delta as a function of omega. So basically, this is just the tangent, di ba? And for different values of Q, okay, so for Q equals 0, medyo straight line siya. Q equals 1, nagsisimula na siyang maging tangent, and as Q approaches infinity, okay, so medyo nagiging ganito yung behavior niya. So meron siyang tawag dito, sharp discontinuity at omega naught. Okay? Okay. So, okay, finally, we can describe yung yung energy, kinetic energy nung particle na driven by a resonant force. So, if we solve for x dot using just the ang tawag dito, using just the particular solution, okay, we get this omega naught squared, omega squared plus 4 omega squared beta squared times sine omega t minus delta. Okay, the kinetic energy then becomes 1/2 mx dot squared. Okay, so this is 1/2 ma squared omega squared over omega naught squared omega squared squared plus 4 omega squared beta squared sine squared omega t minus delta. Okay, and then if you take the average of that, okay, so we're taking the average of the kinetic energy, okay, over one period, okay. So essentially, ang average niyan is 1/2 ma squared omega squared over omega naught squared minus omega squared squared plus 4 omega squared beta squared. And yung average ng sine squared, okay, so sine squared omega t minus delta. Okay, anong average niyan? Okay, sine squared omega t minus delta. Okay, then you take the average of that. Essentially, that's omega over 2 pi 0 to 2 pi sine squared omega t minus delta dt. Okay, so you're considering yung time from 0 to 2 pi over omega, which is one period, di ba? So kinukuha mo yung average ng sine squared function over one period from 0 to 2 pi over omega. Okay, and then this gives us basically 1/2. Okay, which is expected, di ba? Kasi ang sine is this one, okay, and yung sine squared is this one. And if you take the average of that, okay, so the average of that is somewhere here, and that's equal to 1. Okay, so which means that the kinetic energy reduces to the average of the kinetic energy over one period reduces to ma squared over 2 omega squared over 4 omega naught squared minus omega squared squared plus of 4 omega squared beta squared. Okay. Okay, so we have this mathematical treatments of the damped oscillations. Okay, and na next meeting, ang gagawin natin is, of course, magsosolve na tayo ng problems. Okay, and first we'll consider two problems, okay, undergoing oscillatory motion with damping and driving force. And then mag-consider din tayo ng ibang problems, okay, that involve yung classical physics na diniscuss natin from previous chapters. So that's what's going to happen on Tuesday. And then on Thursday next week, okay, I will give you an exercise in advance. Okay, you can find it in the VLE, and we will be meeting face to face. Okay, pero yun nga lang, tulad ng sinabi ko ata to last time, malilate lang ako ng konti, like 6:30 siguro at maximum. So we'll see. So pupunta kayo lahat sa classroom and we'll see each other there in the classroom siguro around 6:30. Okay, and once I get there, I hopefully meron na kayong na-solve ng mga problems, and then you can ask me kung tama yung ginagawa ninyo or kung kailangan ng improvements. Okay?